right, welcome back. And we're going to be looking at section 9.4. And we're going to be learning how to make a decision and a conclusion regarding our hypothesis testing. So think back to our normal distribution curves and our calculators that we use and how these are spread about. And this is showing 98% of the data in the gray region, which would mean there's 0.01, so 1% on the right side and 1% on the left side. So I think we would all agree anything that falls on the left or right side would be considered extremely rare. Top 1%, bottom 1%. And this calculator gives us those values. In this section, we're going to be interpreting the conclusion for all hypothesis testing. And we're going to be looking at these normal distribution curves. And here's another example of a normal distribution curve with showing 1.5% on the top end and 1.5% on the bottom end. So whenever we think about these distributions, we want to think about our hypothesis now. And so the hypothesis, the null hypothesis, means nothing has changed. So the null hypothesis is going to be right down the middle. No change, everything is normal. The alternative hypothesis is going to be in the red regions. That's going to be way on the outside. It's going to be considering something very far away from the null hypothesis. And there's a very low chance that that alternative hypothesis could happen. But if it does happen, then we're going to reject the null hypothesis. So that's kind of what we're working on here. We want to know if we can reject that null hypothesis to accept the unlikely event, the alternative hypothesis. So to do that, we calculate the p-value, and the p-value is our probability. And so if the null hypothesis is true, this results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. A large p-value calculated indicates that we should not reject the null hypothesis. So suppose we're doing a test on just kind of something, anything, and we conclude that there's a 10% chance or a 20% chance that that could happen. Suppose we're flipping a coin a bunch of times and we get heads in a string of heads that we think is unique. Well, but then we test it and they tell us, we find out that that happens 20% of the time, 30% of the time with random data. Well, if something's occurring that often with random data, it's really not that rare. And so if it's not rare, we can't really reject that null hypothesis. So thinking back here, if it happens somewhere in the middle, that's close enough to the null hypothesis, we can't reject it. But if we have a very small p-value, generally 5% or less, then we're going to be over here in the tails. And if we're over there in the tails, we're far enough from the null hypothesis that we might, depending on our levels, we might reject that null hypothesis. And if we reject the null hypothesis, then we have enough evidence to accept the alternative hypothesis. So that's the p-value. The p-value just stands for probability. Okay. So we're going to kind of formalize our decision making. And when we write these, we're going to have our p-value, that's our probability. And then here we're going to have our alpha. And our alpha is just going to be it's going to be a percent or a decimal, and it depends on our problem. Sometimes we will want a really very small alpha for high precision. Sometimes we want a higher alpha. If we're making medicine, you need a really tight tolerance on that medicine. So you want a very low alpha. You don't want it spread out very much. If you're making, our chocolate bar example, that's not as big of a deal as medicine. You can't kill somebody by eating too much chocolate. So that alpha would be a little higher. If our probability is less than our alpha level, then we would reject that null hypothesis. So if our probability is below Let's say our alpha level was maybe like over here, and our probability, or say these are our alpha levels actually. Say our alpha level was right around here, or right here, and our probability was over here, then we would be in the alternative hypothesis zone. So we reject the null hypothesis. So the results of the sample data are significant, there's sufficient evidence, and we kind of always write this conclusion the same way. We say there's sufficient evidence to conclude the null hypothesis is incorrect, that the alternative hypothesis may be correct. If the probability is bigger than or equal to the alpha, then we don't have enough evidence to reject. And that conclusion looks like this. The results are not significant. There's not evidence to, not sufficient evidence to conclude the alternative hypothesis may be correct. Okay. So one quick important point, when we do not reject the null hypothesis, it doesn't mean we've proved the null hypothesis is true. It simply has said that we haven't provided evidence to cast doubt on the truthfulness of the null hypothesis. So we haven't proven it, we just can't reject it. And then here's a little memory device. If the p-value is low, the null must go. So we reject the null hypothesis. And if the p-value is high, the null must fly. Do not reject it. I like to think about this. If the p-value is low, we're going to be in these small regions over here. Therefore, we're far away from the null, so we reject the null hypothesis. Let's try a little example. And this example is kind of cooked up. We'll do a better example in the next video. So we have a lab claiming their procedure improves the chances of being a boy being born. The results for a test for a single population proportion are as follows. So we have the population at 50-50, that's the null hypothesis, and our alternative would be the proportion at 50%, and our alternative would be the proportion is bigger than 50%. So we're trying to prove that they can make a change. And we want an alpha level of 0.01. In the problems, you'll always be given that alpha level. And our p-value is 0.025. So we collect some data, we do some statistical analysis, we find the probability of our data randomly having this connection is 0.025. So that's what, 2.5%. So 2.5% of the time our data will have this connection. But we want a p-value of 1%, 0.01. So we want pretty high precision here. And since the p-value, we compare these two numbers, the p-value is not less than the alpha value. It's close, but it's not less than it. So we cannot reject the null hypothesis. So we don't reject it. So basically, we can't make a conclusion. We're really not sure if this genetic lab is making a difference. Right. And we'll do some better examples in the next video, or more detailed examples, I should say.